What if everything you've been told about the speed of light being the universal speed limit is incomplete? What if, right now, as you watch this video, particles are communicating across vast distances instantaneously, defying everything Einstein told us about reality? In 2022, the Nobel Prize in Physics was awarded for experiments proving that particles can indeed influence each other faster than light should allow. Not theoretically, actually, in real laboratories, with real measurements. Here's the revelation that's going to shake your understanding of reality. We're not asking whether faster-than-light phenomena exist. They do. They're proven. The real question is whether we can harness them to send information, and the answer is so much stranger than a simple yes or no. By the end of this journey, you're going to understand why the universe has to prevent faster-than-light communication, even though faster-than-light connections demonstrably exist. And that reason will fundamentally change how you think about reality itself. Before we dive into this mind-bending journey, hit that like button and subscribe, because you're about to spend 3 hours having your mind systematically reconstructed. Drop a comment telling me what country you're watching from and what time it is where you are. I want to know how far across the globe this information is traveling. And ironically, it's traveling to you at the speed of light right now. But the ideas we're about to explore transcend that limitation in ways you can't yet imagine. Let's start with what we think we know. The speed of light is approximately 299,792,458 meters per second. That's fast, really fast. So fast that if you could travel at light speed, you could circle Earth's equator 7.5 times in 1 second. But here's what's weird. Why is there a speed limit at all? Nothing in our everyday experience suggests that speed should have a maximum. You can always push harder on the gas pedal, always go a little faster. Yet the universe says no, not past this point. Albert Einstein, in 1905, didn't just discover that light speed was the limit. He discovered why it had to be the limit. And the reason is so bizarre that even Einstein himself struggled with its implications for the rest of his life. The speed of light isn't just a speed. It's the speed at which causality itself propagates through the universe. It's the speed of cause and effect. When you flip a light switch, the electromagnetic field changes at your switch, and that change ripples outward through space at light speed. Nothing can go faster, because faster-than-light travel would mean effects preceding their causes. It would mean time travel. It would mean paradoxes that could tear apart the logical structure of reality. Think of it like this. Imagine the universe as a massive computer simulation, and the speed of light is the processor's clock speed, the maximum rate at which the simulation can update from one moment to the next. Everything in this simulation must respect this update rate. If something tried to move faster than the simulation's clock speed, it would be like trying to execute an instruction before the processor has time to process it. The system would break down. But here's where it gets interesting. In 1935, Einstein, working with physicists Boris Podolsky and Nathan Rosen, published a paper that would haunt physics for nearly a century. They described a thought experiment involving two particles that had interacted and then separated. According to quantum mechanics, these particles would remain connected in a strange way. If you measured a property of one particle, you would instantly know the corresponding property of the other particle, no matter how far apart they were. Not just predict it, know it with certainty, because the measurement of one particle would instantly determine the state of the other. Einstein called this Spukhaft Fernwirkung, spooky action at a distance, and he hated it. He hated it because it seemed to violate his own theory. If measuring one particle instantly affected another particle light years away, information would be traveling faster than light. Cause and effect would be happening simultaneously across vast distances. Einstein was convinced this proved that quantum mechanics was incomplete, that there must be hidden variables we weren't accounting for, some deeper reality beneath the quantum weirdness. For decades, this remained a philosophical debate. Then, in 1964, a physicist named John Stuart Bell changed everything. Bell proved mathematically that if Einstein was right, if there were hidden variables determining particle properties in advance, then certain experimental measurements would produce specific statistical correlations. But if quantum mechanics was right, if the particles really were undetermined until measured and really were instantly affecting each other, the statistical correlations would be different. It was no longer philosophy. It was testable. And here's where your understanding of reality starts to crack. In the 1980s and 1990s, physicists including Alain Aspect performed these experiments. And Einstein was wrong. The particles really do affect each other instantaneously. The correlations matched quantum mechanics, not hidden variables. This wasn't a theoretical possibility. This was measured, confirmed, replicated in laboratories worldwide. In 2022, Aspect, Jean Clauser, and Anton Zeilinger won the Nobel Prize for proving this beyond any remaining doubt. So we have faster-than-light connections. They exist. They're real. Particles separated by kilometers, by light years potentially, are influencing each other with no time delay whatsoever. Zero. Instant. And yet, somehow, this doesn't violate relativity. Somehow, this doesn't allow us to send messages faster than light. How is that possible? How can something be instantaneous and yet not allow communication? That question, that apparent paradox, is going to occupy us for the next several hours. And the answer is going to take you deeper into the nature of reality than you've ever been. Stay with me, because every section is going to build on the last. And by the time we're done, you're going to understand not just whether we can send signals faster than light, but why the question itself reveals something profound about the structure of the universe. Let's establish the foundation properly. When we talk about sending a signal, what do we mean? We mean transmitting information. And information, in physics, has a very specific meaning. Information is anything that reduces uncertainty, anything that allows you to know something you didn't know before. If I flip a coin and tell you it landed heads, I've transmitted one bit of information to you. Before I told you, you didn't know which way it landed. After, you did. That's information transfer. Now, for information to transfer, three things must happen. First, there must be a sender who can control what gets sent. Second, there must be a receiver who can detect what was sent. Third, and this is crucial, the sender's choice must affect what the receiver detects. The sender must be able to encode their message in a way that changes the receiver's outcome. Let's apply this to light, the thing we know absolutely can send signals. I have a flashlight. I can turn it on or off. That's the sender's control. You have eyes. You can see whether the flashlight is on or off. That's the receiver's detection. And crucially, my choice to turn the flashlight on or off determines what you see. I can send Morse code. I can send binary. I can send information. Light speed sets the maximum rate at which this information can travel from me to you. Now let's apply this framework to quantum entanglement, a spooky action at a distance. I create two entangled particles. I send one to you, keep one for myself. We separate by a large distance, say a light year. Now I measure my particle. According to quantum mechanics, my measurement instantly determines the state of your particle. The correlation between our measurements is instantaneous. Faster than light could travel between us. But here's the subtle, crucial, reality-shattering detail. I don't control what result my measurement gives me. Quantum measurements are random. When I measure my particle, I might get spin up or spin down, and it's completely random. 50-50 chance. I cannot choose which result I get. And because I can't choose what I get, I can't encode a message. I can't use my particle to send you information, even though my measurement is affecting your particle instantly. Think of it like this. Imagine you and I each have a magic coin. These coins are entangled. Whenever I flip my coin, your coin instantly lands on the opposite side. If mine is heads, yours is tails. guaranteed no matter how far apart we are. The correlation is instant. But I can't control whether my coin lands heads or tails. It's random, so I can't send you a message. If I want to send you heads means yes, tails means no, as an answer to a question, I can't, because I can't make my coin land on the side I want. All you see is a random sequence of heads and tails, and all I see is a random sequence of heads and tails. No information transfer, despite the instant correlation. This is the fundamental principle. Quantum correlations are instant, but quantum measurements are random. You cannot control what you get, so you cannot encode information, so you cannot send signals. Randomness prevents communication, even though connection is instantaneous. But wait, there's something deeply unsatisfying about that explanation, isn't there? Because even though my individual measurement is random, you and I can later compare our results and see that they were perfectly correlated. When I got spin up, you got spin down. Every time. We can verify the faster-than-light connection existed. So in some sense, information did travel faster than light. The information about my measurement's outcome reached your particle instantly. So why can't we use that? Here's where it gets subtle. The information reached your particle, but it didn't reach you. You, the conscious observer, don't know what my measurement result was just by looking at your particle. Your particle's state is determined by my measurement, but you only see a random result. To know that your result was correlated with mine, you need to compare notes with me, and that comparison has to happen at light speed or slower. We have to call each other, send a radio signal, mail a letter, something classical. Only then can we see the correlation. Only then does information reach your conscious mind. The universe is enforcing a strange rule. Quantum systems can connect instantly, but classical information, the stuff conscious minds can access and use, cannot travel faster than light. It's as if reality has two layers. The quantum layer, where connections are instant but inaccessible to us directly, and the classical layer, where information flows at light speed, but is what we actually experience and use. This is a retention hook, a moment to pause and reflect. We've just established that faster-than-light connections exist, but don't allow communication, because quantum measurements are random, and correlations only become visible through slower-than-light comparison. If that seems like a cheat, like the universe is playing a trick on us, you're right to feel that way. And in the next section, we're going to explore attempts to outsmart this rule, to find loopholes in the no communication theorem. And you're going to see just how clever the universe is at preventing information from traveling faster than light, even when physicists design elaborate schemes to try to beat it. The no communication theorem. It sounds like a law against talking, but it's actually one of the deepest principles in physics. It states that no matter how you manipulate entangled particles, no matter what clever scheme you devise, you cannot use quantum entanglement to send information faster than light. It's been mathematically proven. And yet, physicists have spent decades trying to find loopholes because the idea is so tantalizing. Let me describe one of the most famous proposed loopholes, something that seemed like it might work until people analyzed it carefully. It's called quantum dense coding, and it was discovered by Charles Bennett and Stephen Wiesner in the 1990s. Here's the idea. Suppose I have one particle from an entangled pair, and you have the other. I can perform various operations on my particle, different quantum manipulations. These operations will change the overall state of the two-particle system in different ways. If I do operation A, the combined state becomes one thing. If I do operation B, it becomes something else. Now, you receive your particle and make a measurement. Based on what you detect, you can figure out which operation I performed. In principle, I can encode information by choosing which operation to perform. I do operation A for bit value 0, operation B for bit value 1. You measure your particle and determine which operation I did, thus receiving the bit. And here's the kicker. I performed the operation on my particle, and it affected your particle's measurement outcome. That influence was instant, faster than light. So did I just send a faster than light signal? No, and here's why. For you to determine which operation I performed, you need to measure your particle in a very specific way, in what's called the entangled basis. But measuring in the entangled basis is only possible if you have both particles. You need to bring my particle and your particle together and measure them jointly. You can't do it with just your particle alone. And bringing the particles together requires physical transport at light speed or slower. So the information about which operation I performed can only be extracted when the particles are reunited, and that reunion happens at classical speeds. Once again, the quantum connection is instant, but extracting usable information requires slower than light processes. The universe blocks the loophole. Here's another attempt: quantum teleportation. Despite the science fiction name, this is a real, experimentally verified phenomenon. It was first demonstrated by Anton Zeilinger group in 1997. Here's how it works. Suppose I have a particle in some unknown quantum state, and I want to transfer that state to you. We share an entangled pair. I perform a special measurement on my particle from the entangled pair and the particle I want to teleport. This measurement gives me a random result, but it also instantly changes your particle into the state of the particle I wanted to teleport, with some modifications depending on my measurement result. So your particle now has the information from my original particle. The state has been transferred. And that transfer happened instantly, as soon as I made my measurement. Did I just teleport information faster than light? No, because you don't know what modifications were applied to your particle. Your particle is in the correct state, but rotated or flipped in a random way depending on my measurement result, and you don't know which way. To use your particle, to extract the information it carries, you need to know what my measurement result was so you can correct for the modifications. And I have to tell you my measurement result classically, at light speed or slower. Until you receive that classical information, your particle is useless to you. It's in a state that's essentially random from your perspective. So the quantum state teleported instantly, but you can't access it, can't use it, until classical information arrives telling you how to decode it. Faster than light quantum transfer, but light speed information transfer. Are you seeing the pattern? Every single scheme involves quantum processes happening instantly, but requiring classical information transfer to become useful. It's like the universe is taunting us. It's showing us that faster than light connections are real, but building in a fundamental barrier between those connections and our ability to exploit them for communication. But why? Why would the universe be structured this way? What would go wrong if we could send signals faster than light? And here's where we start to get into the really mind-bending territory, because the answer involves time travel, paradoxes, and the possibility that the universe would literally contradict itself. Imagine you have a faster-than-light communication device. You and I are in spaceships, moving relative to each other at high speed. According to Einstein's relativity, we disagree about the order of events. Events that are simultaneous in my reference frame are not simultaneous in yours. And events that are sequential in my frame might be reversed in yours, if they're far apart and separated by faster-than-light signals. Here's the paradox. I use my faster-than-light device to send you a message. From my perspective, I send it at 12 o'clock, and you receive it at 12 o'clock because it's instantaneous. But from your perspective, because you're moving relative to me, my simultaneity is skewed compared to yours. You might receive my message before I sent it. You receive it at 11:50, then at 12 o'clock I send it. Now you use your faster-than-light device to reply to me instantly. From your perspective, you send it 11:50, and I receive it 11:50. But from my perspective, because I'm moving relative to you, your simultaneity is also skewed. I might receive your reply at 11:40. I receive your reply before I sent the original message. Effect before cause. I can send myself a message from the future, and if I can do that, I can create paradoxes. I can send myself a message saying, "Don't send this message," creating a logical contradiction. Did I send the message, or didn't I? If I did, I told myself not to, so I didn't. But if I didn't, I never received the warning, so I did. This is why the universe cannot allow faster-than-light communication. Not just because it breaks Einstein's speed limit, but because it breaks causality itself. It creates logical contradictions that would make reality inconsistent. The universe would become paradoxical, undefined, impossible. And this reveals something profound. The speed of light isn't just a speed limit. It's a causality firewall. It's the maximum rate at which cause and effect can propagate specifically to prevent the universe from becoming self-contradictory. Faster-than-light particles could exist in principle, but the moment they could be used to send information, to create causal chains, they would enable paradoxes. So the universe enforces the no-communication theorem as a fundamental law. Now here's what should blow your mind. This means quantum entanglement, which demonstrably connects particles faster than light, must be structured in such a way that it can never, under any circumstances, be used to send information. Because if it could, the universe would break. The randomness of quantum measurements isn't a bug or a limitation of our knowledge. It's a necessary feature that prevents faster-than-light communication and thereby prevents causal paradoxes and protects the logical consistency of reality. The universe is protecting itself. The structure of quantum mechanics, the fact that measurements are random, the fact that correlations only become visible through classical comparison, all of that is the universe's immune system against paradoxes. Entanglement can exist. Faster-than-light correlations can be real, but they're carefully designed to be useless for communication. This is a major revelation point. We're an hour into this journey, and we've moved from "can we send signals faster than light?" to "the universe fundamentally prevents faster-than-light communication to protect its own logical consistency." Take a moment to let that sink in. The reason you can't send a message to yesterday isn't just a technological limitation. It's a structural property of reality itself. But we're not done, not even close, because there are other phenomena that seem to involve faster-than-light effects, and we need to examine each of them to see whether they offer any loopholes. And in the process, we're going to discover even stranger truths about how the universe works. Let's talk about wormholes. These are theoretical shortcuts through space-time, predicted by Einstein's general relativity. If you could create a wormhole, you could travel vast distances without going through the space in between. From an outside perspective, you'd arrive faster than light could have traveled the long way around. You'd exit the wormhole at your destination before a light beam that took the conventional route would arrive. Is that faster than light travel? Well, yes and no. You didn't actually travel faster than light locally. You traveled through a shortcut where the distance was shorter. It's like asking whether flying from New York to London is faster than driving if there's a magical tunnel through the earth. You got there faster than going around, but you didn't exceed any speed limit along your actual path. But here's the interesting part. If wormholes exist and are traversable, could they be used for faster-than-light communication? Could you send a signal through a wormhole and have it arrive before a light-speed signal sent the conventional way? Potentially, yes. And if so, you could potentially set up the same kind of paradoxes we discussed before. Send a message through a wormhole. Have someone in a different reference frame send a reply through another wormhole. And you could end up receiving a reply before you sent the message. Time travel, paradoxes. So what does physics say about this? Kip Thorne, the Nobel Prize-winning physicist, analyzed this extensively in the 1980s and 1990s. His conclusion: if wormholes exist, if they can be traversed, and if they can be arranged to create closed time-like curves, paths that loop back in time, then quantum effects will destroy the wormhole exactly at the moment it would allow time travel. The universe protects itself again. The mechanism is called vacuum instability. Quantum fluctuations, tiny random variations in the quantum fields, would circulate through the wormhole's time loop infinite times, building up infinite energy and blow the wormhole apart. The wormhole would cease to exist precisely when it became dangerous to causality. It's not that we can't build such a wormhole because we lack the technology. It's that the universe's laws appear to forbid it. The equations suggest that any configuration that would allow sending information to your own past is unstable and self-destructs. This is known as the chronology protection conjecture, proposed by Stephen Hawking. The universe protects the integrity of time. But notice what's happening here. We keep finding that the universe has these built-in safeguards. Quantum randomness prevents faster-than-light communication through entanglement. Vacuum instability prevents time travel through wormholes. It's as if reality has a set of self-consistency rules, and any potential violation triggers a mechanism that prevents it. This leads to a philosophical question. Are these separate coincidences, or is there a deeper principle? Is there some fundamental law that says the universe must be logically consistent, and all these specific mechanisms, quantum randomness, vacuum instability, are just different manifestations of that deeper law? Some physicists think so. They propose something called the principle of self-consistency. It states that the universe can only evolve in ways that are logically consistent with itself. Any potential inconsistency is forbidden, not by specific mechanisms, but by the fundamental structure of reality. The mechanisms we observe, like quantum randomness, are consequences of this deeper principle. If that's true, then asking, can we send signals faster than light, is like asking, can we create a logical contradiction? The answer is no, not because of any specific physical barrier, but because contradictions are not part of reality. The universe is the set of all things that are self-consistent, and anything that would break self-consistency is simply not part of what exists. That's a heavy idea. Let's bring it back to something more concrete. Let's talk about another phenomenon that seems to involve faster-than-light effects, the expansion of space itself. Here's something that's going to surprise you. The universe is expanding faster than light right now. There are galaxies that are receding from us at speeds greater than light speed due to the expansion of space. We can see the effects of this in the redshift of distant galaxies. And yet, this doesn't violate relativity. Why not? Because it's not the galaxies moving through space faster than light. It's space itself expanding, carrying the galaxies along. The rule is that nothing can move through space faster than light, but space itself can expand at any rate. Think of it like ants on a stretching rubber band. The ants crawl along the band at some maximum speed, but the band can stretch faster than the ants can crawl, carrying them apart faster than their maximum crawling speed. Can we use this for faster-than-light communication? If space is expanding faster than light, carrying galaxies along, could we send a signal that rides the expansion? Here's the problem. The expansion of space affects signals the same way it affects everything else. If I send a light beam to a distant galaxy, the light beam travels through space, but space is expanding, stretching the wavelength of the light, redshifting it. The expansion slows down the signal's progress. In fact, there's something called the cosmic event horizon. Beyond a certain distance, space is expanding so fast that light can never reach us from there, and our light can never reach there. Those regions are causally disconnected from us forever. So not only can we not use cosmic expansion for faster-than-light communication, the expansion actually limits our ability to communicate with distant regions. It makes communication harder, not easier. But here's a wild idea. What if we could create expansion locally? What if we could engineer a region of space around us that expands rapidly, carrying us along, while the space in front of us contracts, pulling our destination closer? This is the concept behind the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. The Alcubierre drive is a theoretical warp drive. It doesn't propel you through space. It warps space around you, expanding behind you and contracting in front of you, creating a wave in space-time that carries you along. From the perspective of the space around you, you never exceed light speed locally. But relative to your starting point, you could arrive faster than light could have traveled. Is this possible? The equations of general relativity allow it. Alcubierre showed that such a space-time geometry is consistent with Einstein's equations. But there's a massive catch. It requires exotic matter with negative energy density. And we've never observed such matter. We don't know if it can exist. Moreover, subsequent analysis showed that even if you could create an Alcubierre drive, you couldn't use it for faster-than-light communication in a way that creates paradoxes. The process of setting up the warp bubble and then collapsing it would involve classical signals that respect light speed. And if you tried to arrange two warp drives to create a time loop, you'd run into the same chronology protection issues we discussed with wormholes. Once again, the universe seems to have safeguards. Even when the equations allow something that looks like a loophole, when you analyze it carefully, you find that either it requires impossible materials, or it can't actually be used to violate causality, or both. At this point, we're 2 hours into this journey, and a pattern should be clear. The universe is incredibly clever at allowing interesting phenomena: quantum entanglement, wormhole solutions, space-time warping, while simultaneously ensuring that none of these can be used to violate causality or send information faster than light. Every apparent loophole closes when you look closer. But I want to push further. I want to explore the cutting edge, the speculative ideas that physicists are investigating right now. Because even though the no communication theorem seems airtight, people are still looking for edge cases, extreme conditions, weird scenarios where maybe, just maybe, something slips through. One of the most fascinating areas of current research involves the intersection of quantum mechanics and gravity. We don't have a complete theory of quantum gravity yet, a theory that fully describes how quantum effects and gravitational effects combine. And in that gap, that region of unknown physics, might there be phenomena that change the rules? For example, near a black hole's event horizon, space-time is extremely warped and quantum effects become important. Some physicists have speculated that the combination might allow information transfer in unexpected ways. There's a phenomenon called Hawking radiation, where black holes emit particles due to quantum effects. Stephen Hawking originally calculated that this radiation is completely random, carrying no information about what fell into the black hole. But this led to the black hole information paradox. If information can't escape a black hole, and black holes eventually evaporate through Hawking radiation, where does the information go? Does it get destroyed, violating a fundamental principle of quantum mechanics? Recent work suggests that information might escape through subtle correlations in the Hawking radiation. If so, this is information traveling from inside the event horizon to outside, which naively seems impossible since nothing can escape a black hole. But the information transfer would still respect causality overall. It's not faster than light communication in the sense we've been discussing. It's information encoded in the quantum structure of the radiation in a way that's only accessible by collecting huge amounts of radiation and performing insanely complex measurements. But it raises an interesting question. In extreme conditions, might information find pathways we haven't considered? Might the combination of gravity and quantum mechanics allow for information transfer that circumvents the usual rules? The current consensus is no. Even in quantum gravity, causality protection should hold. The universe should still prevent paradoxes. But we won't know for sure until we have a complete theory, and that's still a work in progress. Another speculative area involves the holographic principle and the structure of space-time at the Planck scale. Some theories suggest that space-time might be emergent, not fundamental. It might arise from more basic quantum information substrates. In such a picture, what we call space and distance might be approximations that break down at the smallest scales. If space-time is emergent, could there be situations where the usual rules about signal propagation don't apply? Could distance become meaningless in certain contexts, allowing instant connections that aren't technically faster than light because the notion of faster assumes space-time exists in the first place? This is highly speculative, but it's being explored by physicists like Juan Maldacena and Leonard Susskind. Their work on the equals EPR conjecture suggests that quantum entanglement and wormholes might be two aspects of the same underlying phenomenon. An entangled pair of particles might literally be connected by a tiny wormhole at the Planck scale. If so, the faster-than-light correlations of entanglement might be explainable as signals traveling through these microscopic wormholes. But even if that's true, it doesn't help us communicate faster than light, because the wormholes would be non-traversable. They'd be too small and unstable to send any usable signal through. They'd explain the correlations, but not provide a communication channel. So once again, even cutting-edge speculative physics doesn't seem to offer a way around the no communication theorem. Let me shift gears and talk about something different: precognition and retrocausality. These are ideas on the fringe of physics, but they've been seriously investigated by a few researchers. The idea is that effects might, under certain conditions, precede their causes. An experiment done in the future might influence results in the past. There have been controversial experiments claiming to show retrocausal effects, like Daryl Bem's precognition studies in psychology. But these have largely failed to replicate and are not accepted by mainstream physics. The reason is that allowing retrocausality would open the door to all the paradoxes we've discussed. However, some interpretations of quantum mechanics, particularly the transactional interpretation developed by John Cramer, suggest that quantum processes involve both forward in time and backward in time influences at a microscopic level. Waves propagate forward and backward in time, and their interaction determines the outcome of quantum measurements. But crucially, these backward influences don't allow you to send information to the past. They're part of the mechanism that produces quantum correlations, but they're not accessible for communication. So even if the universe has some backward in time structure at the quantum level, it's arranged such that we can't exploit it for signaling. The pattern holds. At this point, you might be feeling a bit defeated. Every possible avenue seems blocked. Entanglement? No. Wormholes? No. Warp drives? No. Expanding space? No. Quantum gravity loopholes? No. Retrocausality? No. Is the answer just a simple, definitive no? We can never send signals faster than light. End of story? Not quite. Because there's a conceptual loophole I haven't fully addressed yet, and it's going to lead us into the deepest part of this discussion. The loophole is this: what if sending information isn't as clear-cut as we've been assuming? What if there are ways to influence distant systems faster than light that don't fit the traditional definition of signaling, but still have practical effects? Let me give you an example. Suppose I have a quantum computer here on Earth, and you have a quantum computer on Mars. We share a large number of entangled particles. Now, I perform a computation on my quantum computer using my half of the entangled particles. Your half of the particles instantaneously become correlated with my computation results due to entanglement. In some sense, your particles know what I computed instantly. Now, you can't read out what I computed just by looking at your particles. They still appear random to you. But suppose you're also doing a quantum computation, and you also have entangled particles. By cleverly designing our computations and using entangled resources, we might be able to perform distributed quantum computations that are more efficient than if we were working independently and only communicating at light speed. This is an area of active research called distributed quantum computing. The idea is that even though entanglement doesn't let you send classical information faster than light, it might let you share quantum resources in ways that make joint computations more powerful than they'd otherwise be. Is this communication? Not in the classical sense, but it's a way of correlating activities across space faster than light, and it has practical consequences. We're not sending bits, but we are creating computational advantages through faster-than-light quantum connections. This is subtle, and it's at the frontier of current understanding. It suggests that the question, can we send signals faster than light, might need to be refined. The answer for classical information is clearly no. But for quantum information, quantum resources, quantum computational advantages, the answer might be more nuanced. We can share quantum correlations instantly, and those correlations can have practical effects, even if they don't constitute signaling in the traditional sense. Here's another angle. What about consciousness? Some people have speculated that consciousness might involve quantum effects, and if so, might entanglement play a role in cognition? If your brain and my brain were somehow quantumly entangled, could we share thoughts faster than light? This is highly speculative and not mainstream science, but let's think about it. Even if our brains were entangled, the same rules would apply. The quantum correlations would be random from each of our individual perspectives. For you to know what I'm thinking, you'd need to measure your brain's quantum state and compare it with mine. And that comparison would require classical communication at light speed. So even entangled brains couldn't communicate telepathically faster than light. But here's a wilder idea. What if consciousness isn't localized? What if conscious experience is somehow spread across space through entanglement? What if the you experiencing this moment is quantum mechanically correlated with the me writing this, and with every other conscious system in the universe, in a way that transcends locality? This edges into philosophy and speculation, but it's been seriously discussed by physicists like Roger Penrose and Stuart Hameroff in their orchestrated objective reduction theory. They suggest that consciousness arises from quantum processes in brain microtubules and might involve non-local quantum effects. Even if that's true, it wouldn't allow faster-than-light communication in the way we've been discussing. But it might mean that in some sense, we're all connected faster than light at a deep level. Even if we can't use that connection to send messages, the universe might be more unified, more interconnected than our everyday experience suggests. This brings us to the personal and philosophical implications, which is where we're going to spend the final portions of this journey. We've established the scientific facts. Faster-than-light correlations exist, but can't be used for communication due to quantum randomness and the universe's self-consistency requirements. But what does that mean for you? How should it change your worldview? First, consider what quantum entanglement tells us about the nature of reality. Two particles can be separated by billions of light years and still be instantaneously correlated. This isn't just a quirky fact about particles. It's a statement about the fabric of reality itself. It means that separateness, the idea that things far apart are independent, is an illusion at some fundamental level. Think about what this means for your place in the cosmos. Right now, as you watch this video, you are made of particles. Trillions upon trillions of them. And many of those particles have interacted with other particles throughout history. Particles that are now part of other people, other planets, other stars. In principle, there are quantum correlations connecting you to everything that you or your constituent particles have ever interacted with. You are entangled with the universe. Now, before you get too excited, remember, you can't access these correlations directly. You can't feel them or use them. From your everyday perspective, you're still a localized being in one place at one time. But at the quantum level, you're connected to everything in ways that transcend space and time. The boundaries between you and the rest of the universe are not as solid as they seem. This should genuinely blow your mind. The Newtonian worldview was that the universe is made of separate objects bouncing off each other like billiard balls. Einstein refined this by showing that space and time are relative and interconnected. But quantum mechanics goes further. It says that objects themselves are not fundamentally separate. Two particles that have interacted remain part of a single quantum system forever, no matter how far apart they move. The whole universe is, in a sense, one gigantic entangled quantum state that we've been dividing into separate objects only because that's how our senses work at the macroscopic scale. John Bell, the physicist who proved that entanglement was real and not explainable by hidden variables, said this: "The concept of locality is the enemy of the quantum." What he meant was that quantum mechanics fundamentally challenges the idea that reality is local, that things only affect their immediate surroundings. Quantum mechanics is telling us that the universe is non-local at its core. But here's the paradox. Despite this non-locality, causality is still local. Effects still propagate at light speed. Information still transfers at light speed. So we have a universe that is non-local in its structure, but local in its behavior. The connections are there, but we can't use them. Why? And this is where we get to the deepest insight of this entire exploration. Because if we could use them, if we could send information through entanglement, we could send information to our own past, creating paradoxes. And those paradoxes would make reality inconsistent, undefined, impossible. The universe has to be non-local because quantum mechanics works the way it does. But the universe also has to prevent us from using that non-locality for communication, because otherwise causality breaks down. So quantum randomness, the fact that measurements give unpredictable results, is the compromise. It's the mechanism that allows non-local correlations to exist while preventing them from violating causality. In other words, the universe is fundamentally connected, but those connections are hidden behind randomness to protect the logical consistency of time and cause and effect. We live in a universe that is deeply unified but appears fragmented, and that appearance is necessary for reality to work. Let that sink in. The randomness of quantum mechanics, the thing that bothered Einstein so much that he said, "God does not play dice with the universe," is not a flaw. It's a feature. It's the price the universe pays to be both non-local and causal at the same time. Without randomness, without the uncertainty principle, the universe would either have to give up non-locality, meaning quantum mechanics wouldn't work, or give up causality, meaning time travel paradoxes would be possible. God does play dice, Einstein, but for a very good reason. The dice protect the integrity of time itself. Now let's bring this to an even more personal level. You might be thinking, okay, so quantum entanglement connects everything, but I can't use it, so what does it matter to me? And that's a fair question. Let me tell you why it matters. First, it should change how you think about connection and separation. We often feel isolated, disconnected from others, from nature, from the universe. We feel like separate beings in separate locations, interacting only when we bump into each other physically or send signals. But quantum mechanics reveals that underneath that appearance, there's a deeper reality where everything that has ever interacted remains connected forever. Yes, you can't consciously access those connections, but they're there. You are literally, physically, quantum mechanically connected to every person you've ever met, every place you've ever been, every object you've ever touched. Those connections persist. They're real. They're part of the physical structure of the universe. This should make you feel less alone. Even when you're by yourself, even when you're isolated, you're embedded in a web of quantum correlations that links you to the entire history of everything you've experienced. The universe remembers your connections, even when you don't. Second, this should change how you think about information and knowledge. We tend to think of information as something that's either here or there, something that moves from place to place at specific speeds. But quantum information doesn't work that way. Quantum information can be delocalized, spread across entangled particles in multiple locations simultaneously. The information isn't in any one place. It's in the correlations between places. This suggests that at the deepest level, information isn't a substance that flows. It's a pattern of relationships. And those relationships can be non-local. Knowledge, understanding, the structure of reality itself, these aren't localized things. They're patterns in the quantum state of the universe, patterns that transcend individual locations. What does that mean for consciousness, for your mind? Well, your brain is a physical system made of quantum particles. The information in your brain, your memories, your thoughts, your sense of self, is encoded in quantum states and their correlations. In principle, that information is non-local too. It's not just in your brain. It's in the quantum correlations between your brain and everything it has interacted with. Now, I'm not saying your consciousness literally extends outside your brain. That would be a leap too far with current science. But I am saying that the physical basis of your consciousness, the quantum information that constitutes your mind, is entangled with the universe in ways we're only beginning to understand. You are not an isolated computational system. You're a node in a vast quantum network. Third, and this is perhaps most profound, the fact that the universe prevents faster-than-light communication to protect causality means that the arrow of time, the flow from past to future, is not just a human perception. It's built into the structure of reality at the deepest level. The universe cares about cause preceding effect. The universe has a temporal direction. Why should the universe care? Why should there be an arrow of time at all? This is one of the deepest unsolved problems in physics. The fundamental laws, like quantum mechanics and relativity, are mostly time-symmetric. They work the same forwards and backwards in time. Yet the universe has a clear arrow. Entropy increases. Effects follow causes. We remember the past, but not the future. The no communication theorem and the causality protection mechanisms we've discussed give us a clue. The universe prevents paradoxes. It prevents situations where effects precede causes. It does this through randomness, through vacuum instability, through various mechanisms that all point in the same direction. Time must flow consistently from past to future. This suggests that the arrow of time might be related to logical consistency. The universe flows forward in time because flowing backward or allowing loops would create contradictions. Time's arrow is reality's way of being self-consistent. And here's where it gets personal. You exist in time. You have a past and a future. You make decisions that affect what happens next. And all of that is only possible because the universe enforces causality, because it prevents paradoxes, because it has an arrow of time. If faster-than-light communication were possible, if you could send signals to your own past, your free will would become paradoxical. You could receive a message from your future self telling you what you're going to do, and then choose not to do it. But if you don't do it, your future self never sends the message. Contradiction. Your ability to make meaningful choices depends on the future being open, not predetermined by messages from that same future. The no communication theorem protects your free will. By preventing information from traveling to the past, the universe ensures that your future is not constrained by messages from that future, allowing it to be genuinely open to your choices. This is a staggering realization. The same principle that prevents faster-than-light communication, the principle of causal consistency, is also what makes your life meaningful. It's what allows you to make choices that matter, to affect the future without the future reaching back and constraining you. The universe is structured to be self-consistent, and that structure creates space for agency, for consciousness, for you to be a genuine cause in the world rather than just an effect. Let me take this even further into implications for meaning and purpose. We've established that you're quantum mechanically connected to everything you've ever interacted with, but you can't use those connections to communicate faster than light. What you can do is affect the future through your choices and actions at light speed or slower, through normal causality. This means that your influence on the universe propagates outward at light speed. Every action you take, every word you speak, every thought you think that leads to an action sends ripples through spacetime at light speed. Those ripples affect other people, who then affect others, creating an expanding wave of causality that emanates from you. Right now, as I create this video, my actions are affecting you. Information is traveling from me to you at light speed through the internet infrastructure, through fiber optic cables and electromagnetic waves. That information is changing the state of your brain, creating new thoughts, new understanding. And those new thoughts will lead you to take actions that affect others, creating further ripples. You are a source of causal influence spreading at light speed. And because the universe has been around for 13.8 billion years, and because influences can compound and cascade, the ultimate reach of your actions is potentially vast. Everything you do sends ripples into the future, and those ripples can, in principle, affect the entire future light cone of your life, the region of spacetime that you can causally influence. Your life, your choices, they matter causally. They matter physically. They're part of the causal structure of the universe. And while you can't send signals faster than light, you can send signals at light speed, which means you can affect the future of the entire observable universe given enough time. But there's a limit. Because the universe is expanding, and that expansion is accelerating, there's a cosmic event horizon. Beyond a certain distance, space is expanding so fast that light from there can never reach us, and our light can never reach there. Those regions are causally disconnected forever. This means that your causal influence has a maximum extent. There's a boundary to how much of the universe you can affect, no matter how long you live or how clever you are. The expansion of space limits the reach of causality itself. And here's what's beautiful and tragic about that. Within your causal horizon, within the region you can affect, you matter infinitely. Your choices echo through time, affecting chain reactions of events. But beyond that horizon, you're irrelevant. Those regions don't know you exist and never will. This should make you appreciate the connections you do have. The people within your causal horizon, the people you can reach and affect, they're precious because they're the only ones you'll ever be able to touch. The universe has drawn a boundary around you, a sphere of influence beyond which you cannot reach, and everything inside that sphere is your domain, your responsibility, your opportunity to make a difference. The no communication theorem isn't just about faster than light signals. It's about the structure of connection and influence in the universe. It tells you that you're deeply connected quantum mechanically to everything you've touched, but you can only influence things causally at light speed or slower. And that combination, connection plus limited influence, creates the conditions for meaning. If you could affect everything instantly, if faster than light communication were possible, nothing would be distant, nothing would be out of reach, and in a strange way, nothing would be special. The limitations create value. The fact that you can't affect everything makes the things you can affect meaningful. Let's talk about the future. Where is research on this topic heading? What questions remain open? One major area is quantum gravity. We still don't have a complete theory that unifies quantum mechanics and general relativity. And in that gap, there might be surprises. Some physicists speculate that at the Planck scale, the smallest scale where both quantum effects and gravitational effects are important, space-time itself might dissolve into something more fundamental. And in that regime, the usual rules about causality and signal propagation might be different. But even if that's true, most physicists expect that causality protection will still hold. The universe might have a different structure at the Planck scale, but it will still prevent paradoxes. The mechanisms might be different, but the outcome, no faster than light communication, will likely remain. Another area is quantum computing and quantum information theory. As we build more powerful quantum computers and quantum networks, we're learning to manipulate entanglement more precisely. And we're discovering subtle ways that entanglement can be used as a resource. We can't send classical information faster than light, but we can use entanglement to do things like quantum key distribution for secure communication, quantum teleportation for transferring quantum states, and potentially distributed quantum computing for enhanced computational power. These applications don't violate the no communication theorem, but they push the boundaries of what we can do with quantum correlations. And as we push those boundaries, we might discover new effects, new subtleties, new ways that entanglement connects things that we hadn't appreciated before. There's also ongoing philosophical debate about what quantum entanglement means for the nature of reality. The Copenhagen interpretation says that quantum systems don't have definite properties until measured. The many worlds interpretation says that all possible measurement outcomes happen in different branches of reality. The pilot wave interpretation says there are hidden variables, but they're non-local, with faster-than-light influences that happen to average out, so we can't use them for communication. Each interpretation gives a different picture of what's really happening with entanglement. But remarkably, they all agree on the observational predictions. They all agree that you can't use entanglement to send information faster than light. The no communication theorem is interpretation independent. It's true no matter which interpretation of quantum mechanics you prefer. This suggests that the no communication theorem is more fundamental than the interpretations. It's a constraint that any correct description of reality must satisfy, regardless of the underlying metaphysics. The universe doesn't care what you think is really happening as long as you obey the rule. No faster than light communication. So where does that leave us practically? Are there any technologies on the horizon that come close to faster than light communication, even if they don't technically violate the rules? One possibility is quantum networks. Imagine a future where we have quantum internet with entangled particles distributed across the globe and beyond. You could perform quantum teleportation instantaneously, but you'd still need to send classical information at light speed to complete the protocol. However, having entanglement pre-distributed means that when you do need to teleport a quantum state, the quantum part is instant. Only the classical part is delayed. For certain applications, this could be advantageous. For example, in quantum cryptography, having entanglement allows you to share encryption keys that are provably secure. An eavesdropper trying to intercept the key would disturb the entanglement in a detectable way. This doesn't let you communicate faster than light, but it does give you security guarantees that are impossible with classical communication alone. Another possibility involves using the quantum structure of space-time itself. Some theories suggest that the vacuum, empty space, is actually seething with virtual particles popping in and out of existence due to quantum effects. These vacuum fluctuations might be manipulable in ways we haven't discovered yet. If we could somehow engineer the vacuum, create regions with different vacuum energy, we might be able to affect how signals propagate. But again, current theory suggests that even if we could do this, we couldn't violate causality. We might be able to do interesting things with signal propagation, but the light speed limit would remain in some form. There's also speculative ideas about using dark energy or dark matter, the mysterious components that make up most of the universe's mass and energy. We don't know what they are, but they have unusual properties. Dark energy causes the universe's expansion to accelerate. If we could manipulate dark energy, could we do things we can't currently imagine? Maybe. But again, the principle of causality protection suggests that even if dark energy allows exotic phenomena, it won't allow faster-than-light communication that creates paradoxes. The universe has been very consistent about this rule, and there's no reason to expect it to change just because we discover new physics. One more area worth mentioning: analog systems and effective faster-than-light propagation. In certain materials, sound waves or other disturbances can propagate at different speeds depending on the medium's properties. In some cases, You can create situations where a signal appears to travel faster than light, but it's really traveling faster than light within that medium, not faster than light in vacuum. For example, in some optical materials, you can create pulses of light that appear to travel faster than the vacuum speed of light. But careful analysis shows that these are not carrying information faster than light. They're artifacts of how the pulse is shaped and how the medium responds. The actual information, the part you could use to send a message, still travels at or below the vacuum light speed. These are interesting phenomena, and they teach us about wave propagation and information theory. But they're not loopholes in the fundamental speed limit. They're examples of how complex the relationship between signals, waves, and information can be. At this point, we're approaching the 3-hour mark, and I want to bring everything together. Let's recap the journey we've taken. We started with the shocking revelation that faster-than-light correlations exist. Quantum entanglement is real, proven, Nobel Prize-winning physics. Particles separated by vast distances are instantaneously connected in ways that Einstein himself found deeply troubling. We then explored why these correlations can't be used for communication. Quantum measurements are random. You can't control what you get, so you can't encode a message. The correlations only become visible when you compare results classically at light speed or slower. And this isn't a technological limitation. It's built into the structure of quantum mechanics itself. We examined attempted loopholes, quantum dense coding, quantum teleportation, wormholes, warp drives, expanding space, quantum gravity effects, retrocausality. In every case, we found that either the loophole doesn't actually work, or it requires impossible conditions, or it's blocked by some physical mechanism like vacuum instability. The universe is remarkably consistent in preventing faster-than-light communication. We discovered the reason: causality protection. If faster-than-light communication were possible, you could send signals to your own past, creating logical paradoxes that would make reality inconsistent. The universe prevents this through various mechanisms, all of which ensure that cause precedes effect. We realized that quantum randomness, the thing Einstein hated, is actually a necessary feature. It's the mechanism that allows non-local quantum correlations to exist, while preventing them from violating causality. The universe is non-local in structure, but local in causal behavior, and randomness is what makes that combination possible. We explored the personal implications. You are quantum mechanically connected to everything you've ever interacted with, but you can only influence the future causally at light speed or slower. This creates a sphere of influence, a causal horizon within which you matter infinitely. The limitations on communication create the conditions for meaning and agency. And we looked at the frontiers of current research, where physicists are still exploring the boundaries of what's possible with quantum information, quantum networks, and exotic space-time geometries. But in all cases, the principle of causality protection seems to hold. So here's the final answer to the question we started with. Can we send signals faster than the speed of light? No, not in any way that would allow you to communicate information faster than light. The universe fundamentally prevents this to protect its own logical consistency. But that no comes with an asterisk. Because there's a deeper truth, the universe is non-local. Connections exist that transcend space and time. You are entangled with everything you've ever touched. And while you can't use those connections to send messages, they're real, they're physical, and they make you part of a cosmic web that extends across the universe. You live in a reality that is deeply unified at the quantum level, but appears fragmented at the classical level. And that fragmentation, that inability to access the unity for communication, is what makes time flow consistently forward, what makes your choices meaningful, what makes your influence on the future a real causal power rather than a paradoxical loop. The speed of light is not just a speed limit. It's the rate at which causality propagates. It's the frame rate of reality. It's the clock speed of the universe's computation. and it's set precisely to the value that allows the universe to be both quantum mechanically connected and causally consistent. Here's what I want you to take away from this 3-hour journey. You cannot send signals faster than light, but you are connected to the universe in ways that transcend light speed. Those connections are hidden behind quantum randomness to protect causality. And that protection is what makes your life meaningful, your choices real, and your future open. The universe is stranger than we imagined, more connected, more unified, but also more carefully structured to prevent paradoxes. We live in a cosmos that is fundamentally non-local, but phenomenally local, and that paradoxical combination is what makes reality possible. Every action you take sends ripples through space-time at light speed, creating cascades of causality that can affect the entire future within your light cone. You matter causally. You matter physically. You're a node in the causal network of the universe, and while you can't reach beyond your cosmic horizon, everything within it is touched by what you do. So the next time you send a message, whether it's a text to a friend or a signal to a spacecraft, remember that information is traveling at the maximum possible speed for causal influence. It's traveling at the speed of reality itself. And while you can't go faster, you don't need to. Light speed is fast enough to span the entire reachable universe, even time. The universe has drawn boundaries, but within those boundaries, you have infinite creative potential. You can't break the rules, but the rules are generous enough to give you a vast playground. Faster than light communication is forbidden, but light speed communication is allowed, and that's enough to touch everything you'll ever be able to touch. Before we close, let me tell you about one final mind-blowing fact that ties everything together. It comes from information theory and quantum mechanics. There's a principle called Bekenstein bound, formulated by physicist Jacob Bekenstein in the 1970s. States that there's a maximum amount of information that can be contained in a given region of space. And that maximum is related to the area of the region's boundary, not its volume. This led to the holographic principle, the idea that all the information in a 3-dimensional region of space can be encoded on its 2-dimensional boundary. The universe might be fundamentally 2-dimensional, with the 3rd dimension being an emergent property of the information encoded on the surface. If that's true, then the notion of distance inside the volume is derivative. What's fundamental is the information on the boundary. And if space itself is emergent from information, then the speed of light might be emergent too. It might be the natural speed at which information propagates in the emergent spacetime. This suggests that the speed of light isn't arbitrary. It's not just a constant we happen to measure. It's the speed at which information naturally flows in a universe where space emerges from quantum information. And the no communication theorem, the rule that you can't send information faster than light, might be equivalent to saying that you can't violate the structure of the emergent spacetime itself. In other words, asking, "Can we send signals faster than light?" is like asking, "Can we violate the fundamental structure of space and time?" And the answer is no, because space and time are what they are in virtue of how information flows. Changing the speed of information would change the nature of space-time itself, potentially making it inconsistent or non-existent. This is the ultimate answer. We can't send signals faster than light because doing so would be tantamount to existing outside of space-time, outside of reality itself. The speed of light is the speed of existence. It's how fast reality happens. And we're inside reality, made of it, governed by it. We can't step outside the universe to send signals at a different speed because there is no outside. You are made of information flowing at the speed of light, encoded in quantum states, entangled with the universe, propagating causally through an emergent spacetime. You are not separate from reality. You are a pattern in reality, a structure in the flow of information, a node in the causal network. And that's not a limitation. That's what you are. That's what it means to exist. So can we send signals faster than light? No, but we are signals, traveling at the speed of light through the universe, creating ripples, affecting the future, mattering causally and quantum mechanically in ways both seen and unseen? You are light speed information given form and consciousness. And that's extraordinary enough. Thank you for spending these 3 hours with me on this journey from quantum entanglement to the nature of causality to the meaning of your existence. If this changed how you see reality, hit that like button. If you want more deep dives into the nature of the universe, subscribe. And drop a comment telling me, do you think we'll ever find a way around the no communication theorem? Or is causality protection truly fundamental? I want to hear your thoughts. Remember, the universe is stranger than we can imagine, but it's also more carefully structured than we give it credit for. Every rule has a reason. Every limitation serves a purpose. And the purpose of the speed of light limit is to keep reality self-consistent, to keep time flowing forward, to keep your choices meaningful, and to keep existence possible. You live in a universe that cares about consistency, that protects causality, that enforces the arrow of time. And that's why you can make choices, have effects, and matter. The universe won't let you send signals faster than light, but it will let you be a signal, traveling at light speed, echoing through time, affecting everything in your future light cone. And that's enough. That's everything. See you in the next video, where we'll explore another question at the edge of human understanding. Until then, keep questioning, keep wondering, and keep being the light speed pattern of information that you are.